Richard James Mathematics Resources will now present Grade 4 Practice Paper 2, Part B. Do not forget that in these video presentations, we have the videos divided into 4 parts, A, B, and C. Parts A, B, and C each has 12 problems to solve. And no doubt this one will have 12 problems also. We will begin the second group of 12 problems, and this one will begin at problem number 13. So let us take a look at problem number 13. Of the 134 plums in a box, 27 were eaten and 10 were spoiled. How many plums were left? Now, you have to consider that if you have 134 plums and you eat 27 of them, then the number of plums will decrease. You also consider that if you have 10 of them that were spoiled, that will also further reduce the number of plums that you have. So you will be going down in your numbers because you would have eaten 27 of them. And also you will go further down because 10 of them were spoiled. Because of that, what will we do? What kind of mathematics process or operation or arithmetic operation we will carry out in order to demonstrate that the number of plums were reduced? So there we have, to begin with, your 134 plums. 27 of them were eaten. If 27 of the plums were eaten, it means that the number is getting less. We therefore need to subtract those 27 plums. So we need to take away 27 from 134. We cannot take 7 from 4 in that manner, so we go to the greater place value and rename the 3. Do not forget that if we are at a particular place value, then the place value to the left of that one is 10 times the place value that we have here. So the place value to the left is always 10 times the present place value. So we rename this 3, removing 1 from here. That's 2. But it is 10 times the one that we remove right here, because it is of the greater place value. It is 10 times the place value that we have here. So instead of 1 being added to this 4, we have 10 added to the 4. So 10 plus 4 is equal to 14. But instead of writing 14 separately, we have to make use of the space that we have there. So the 1 is written somewhat smaller in order that we can accommodate it. But what we really mean is that this is 14. Why is it 14? Because we remove 1 from the place value of greater significance. And that greater significance place value is 10 times the present place value. So we know that the one that we remove from here is actually 10 times what we have here. So this turns out to be 10, this one that we have right here. So we intend to write 14, but space does not allow us because we have the other digits to contend with. So we write the 1 small right here, but we are indicating that it is actually 14. So we say 14 minus 7, and that is equal to 7. Also, 2 minus 2, that's 0, and with nothing to take away from 1, it returns as it is. So we have 107 plums remaining after eating 27 of them. 10 were spoiled. What do we do with those spoiled plums? The 10 spoiled plums must also be taken out, which further reduces the number of plums. We will subtract 10 from the remainder. So the remaining plums, 107, 10 of these were spoiled. Therefore, we need to remove those spoiled plums. So we will subtract 10 right there. And of course, we will say 7 minus 0, that is 7. And we intend to say 1 from 0, we can't. And if we go here and rename the 1, it is the same thing, or the same effect, as if we say 1 from 10. 10 subtract 1, or 10 take away 1, and that will give us 9. Now, Jerry is not here as yet. So Jerry Lewis is not present as yet. So he's not the one who got the opportunity to eat those 27 plums, although he wouldn't mind. So we just have to proceed without Jerry Lewis enjoying this problem that has to do with someone eating 27 plums. When he returns, I imagine that he will be here in time before the conclusion of this video presentation so he can make his contribution. But I'm happy that he's not going to be able to see this plum eating problem. The correct answer is option C. Now, we will take another approach to the problem. Of the 134 plums in a box, 27 were eaten and 10 were spoiled. How many plums were left? Another way to solve the problem is to first add together those plums that have been taken out, because 27 were eaten and 10 were spoiled. So all of those plums were taken out. So those plums will serve to reduce in total the number of plums. So we will take an approach in which we will add together all of the plums that were taken out, and then we may take that number away from the total number of plums. So we have 7 plus 0 is equal to 7, and 2 plus 1 is equal to 3. So we have 37 plums were removed. And we will take away 37 from 134. So instead of taking away 27 and then taking away 10, we may put the 27 and the 10 together and take those, or the total of those, from 134. We cannot take 7 from 4, so we go to the greater place value and rename the 3. What will happen? 2 goes there, and do not forget that the place value to the left is always 10 times the present place value. So we are actually taking 1 from here, but because it is 10 times this place value, it is placed here as 10. Not only that, we are adding the 10 to the 4, and we have 14. And we really intend to write 14, but because of the space that we have occupied by the other digits, we will just put this one in a very reduced size. But it is 14. 14 minus 7 is 7. And what do we intend to do? We intend to take 3 from 2. We cannot do that in this mode of subtraction. So we will go to this 1 and rename it. If we rename this 1, we will have 12 right here. And if we cause it to remain, we only have 12 left. So whether we rename or we cause it to remain, the effect is the same. So we will go straight ahead and subtract 3 from 12, and the result is 9. In this mode of subtraction, we cannot take 3 from 2. There is only 1 at the other place value. Whether we rename or not, it will be the same effect as saying 12 minus 3 is equal to 9. The correct answer is option C, and we realize that is exactly the same as in the previous take on the problem. Austin's mother bought 8 cases of soda for a party. There were 24 cans in each case. How many cans of soda did she buy? Austin's mom bought 8 cases of soda for a party. There were 24 cans in each case. How many cans of soda did she buy? 8 cases, 24 in each. How many in all? 8 cases, 24 in each. How many in all? So there is your case of soda. There is your case of soda. There we have our case of soda. How many cans in each case? The statement of the problem says 24, but we may make a quick check without counting them. So we can make a quick check. We do not have to count them 1, 2, 3 all the way to 24. Count the number of cans that are along the width and the number of cans that are along the length. So along the width we have 4 cans. Along the length we have 6 cans. Multiply those two numbers. 6 multiplied by 4, and the result is 24. 6 fours, 24. And we may take that approach in any situation that we have a particular number, especially in a rectangular arrangement in which we have a particular number going in one direction and another number going in the other direction. Instead of counting them individually, we can say it is 4 by 6, and that's 24. 6 by 4 is equal to 24. And that is a small number to count to. But if you can see the two numbers at a glance, you can check. Your check is over in a flash. Also, the method may be extended to situations in which the numbers are large. For example, 200 by 7. So if you have something that is 200 by 7 and you need to know the number of individuals within that, then you know that you multiply 200 by 7 and you quickly get 1,400. As a matter of fact, you will be just counting to 207, but the number of them will be 1,400. So it will take a very much longer time to count to 1,400 than to recognize that it is 200 by 7. Therefore, it is 1,400. Austin's mom bought 8 cans of soda for a party. There were 24 cans in each case. How many cans of soda did she buy? Now we have that first case of soda. There we have a case of 24 cans of soda. Another case will give us twice the number of cans that are in one case. So we have 2 cases. So the number of cans will be 2 times the number of cans that we have in one case. And if we put another case, then what? A third case will give us 3 times the number of cans that are in one case, and so on. Therefore, the number of cans in 8 cases will be 8 times the number of cans that are in one case. Any number of events or objects that we have occurring a certain number of times, to find the total number of occurrences, we will multiply those numbers. So if we have 24 occurring 8 times, the total number will be 24 times 8. So we will therefore multiply 24 by 8. And throughout your lessons, you will hear your teacher using the word times when he or she means multiply. For example, 24 times that by 8. When she means 24, multiply that by 8. Or she will say 6 times 5. When she means 6 multiplied by 5. And we have our multiplication table. And what do we call our multiplication tables? We call them times tables. So when something occurs a particular number of times, then according to our normal mode of speaking in the classroom, then we times the two numbers, or we multiply the two numbers. So we will multiply 24 by 8. So 8 fours, 32. When multiplying numbers, we begin with the numbers at the right. They are the ones with the smallest place values. So we will multiply 8 by 4 first. And as we stated before, that's 32. And what do? We write 2 in the ones column and carry 3 to the tens column. What we intend to do is write down the entire 32. But if we do so, then when we multiply 8 by 2, it's the 3 that we have here will get in the way of the result. Not only that, it has to be added to the result. So we know that it will fall in the tens column, which is the column of greater significance. So we carry that to the top of the column in order that it does not get in our way. So we carry the 3 to the tens column. Then what do? We say 8 times 2, and that's 16. But do not forget the 3 that we have here. So we add the 3 to the 16. We get 19. And we intend to just put 9 down and carry 1 to the hundredths column. We do not normally do that in our classroom because we do not have another number to multiply. We'll just put down the 19. But I am just showing that in actuality it is carried to the other column. And with nothing to multiply, then it is the only thing present in that column, and we'll have to take its rightful place in the product. No other number to be multiplied. The one that was carried to the hundredths column will be the hundreds digit. And we may have written it down some while ago, but we are just making use of the fact that it was actually carried to the hundredths column. In any way that you choose, then you are not going to be theoretically incorrect. So you may write it down at once, or you may treat it as a carry. The correct answer is option A. John ate 3/4 of a cake and gave away 1/4 or a quarter. How much does he have left? John ate 3/4 of a cake and gave away 1/4. How much does he have left? The 3/4 and a quarter that we have there in the statement of the problem are indicators that the cake is divided into quarters. What are quarters? A quarter is one of the 4 equal parts of a whole. It therefore means that the whole needs to be divided into 4 equal parts. But before we do that, we know that if John ate 3/4 and gave away 1/4, that 1/4 with 3/4, when we add these together, we will get 4 quarters. And 4 quarters will make 1 whole. Therefore, John ate 3/4 and gave away a quarter. That being the case, it means that there is no cake left, and the answer is option D. So students could work that out in their minds, and as a matter of fact, that is what I would expect for someone in the grade 4 examination. However, for every problem that we solve, I am taking the opportunity to present fundamental mathematics principles, and I am sorry that at this time Jerry is not present as yet. So a quarter is one of the 4 equal parts of a whole. It therefore means that the whole needs to be divided into 4 equal parts. So we have the whole divided into 4 equal parts, and we have 1/4 represented right there, and we are taking a look at the parts of the fraction, the numerator, the fraction bar, and the denominator. There we have a quarter. The denominator tells us the number of parts that the whole is divided into. The whole is divided into 4 equal parts. We have 4 equal parts. The denominator of the fraction is actually 4. And if the denominator is 4, that means the whole is divided into 4 equal parts. The numerator tells us the number of those equal parts that we are talking about. John ate 3/4 of the cake. It means that 3 of those equal parts out of 4 were taken out. So John ate 3/4. 3 of those quarters, meaning 3 of those equal parts of the whole, were taken out. So those are gone. 3 of them were taken out. John ate those 3 parts. He gave away 1 part, 1/4. We only have 1 part left out of the 4 equal parts. If we give away that 1 part, none will be left. The correct answer is option D. But give it away nonetheless. So let us give it away. There it goes. Gone. So how many of those equal parts are left? 0. And 0 out of 4 is still 0. So the amount of the cake that is left is 0. On the next slide, use arithmetic to solve the problem. We will take the whole cake, eat 3/4, then give away a quarter. The whole cake is divided into 4 equal parts. The whole represents 4 parts out of 4 equal parts, which is 4/4 or 4 quarters. And Jerry is missing the cake eating, and he also missed the plum eating. So maybe Jerry imagined that he would get here this morning with the opportunity to have a lot of stuff to eat, but he would have missed those two problems. That's the reward for arriving late. John ate 3/4 of a cake and gave away 1/4. How much does he have left? So there we have the entire cake represented by 4/4 or 4/4. There we have our whole cake. 4 parts out of 4 equal parts. That's the entire cake. 4 parts. All 4 parts of the 4 equal parts. We need to subtract the 3/4 that John ate. He ate 3/4. Let us take that away. Subtracting fractions with the same denominator, the answer will have the same denominator as the fractions. So put the denominator of the answer. It will be the same as the denominator of the fractions that we have. When we are subtracting or adding fractions that have the same denominator, the answer will have the same denominator as the fractions. The resulting numerator will be the difference between the two numerators. So the final numerator will be obtained by subtracting the numerators. So we have 4 minus 3 and 4 minus 3, Jerry. That's equal to 1. So we have 1/4 or just a quarter left. Gave away a quarter. A quarter was given away. We need to subtract a quarter from the result. So that's the answer when we would have subtracted 3/4. Of the remaining cake, which is a quarter, we still need to subtract a quarter. And in mathematics, we know that if we subtract one number from itself, the result is 0. Any number subtract the same number, the result is 0. But we will do our subtraction nonetheless. The answer will have the same denominator as those two fractions. Each of them has a denominator of 4. So the denominator of the result will be 4. And the numerator will be obtained by subtracting the numerators. 1 minus 1. And the result is 0. And 0 over 4 is the same as 0 divided by 4. And 0 divided by any number, the result is 0. But if we divide 0 by 0, then we have some difficulties that will be discussed at a greater grade level. So 0 divided by 4 is equal to 0. Any number that you divide into 0, the result is 0. As long as that number is not equal to 0, when we have the number that we are dividing by is equal to 0, then we run into trouble. The correct answer is option D. In the recent problem, we have divided the circle that represented the cake into quarters. They are actually quarters because the 4 parts are equal. So we have quarters right there because the 4 parts are equal. Here again, we will proceed to divide the cake into 4 parts. Are they quarters? I have nobody to answer today. I will have to answer for myself. Are they quarters? No. they are not quarters. Why is it that they are not quarters? They are not quarters because they are not equal in size. So they are of different sizes. They are not quarters. So if we divide this into 4 parts, that does not make each part a quarter. For it to be a quarter, all of the parts have to be equal. They are not quarters because they are not all of the same size. For the 4 divisions to be classified as quarters, they have to be equal. As we have seen, it is possible to divide a shape into 4 parts that are not equal. And we have 4 parts here that are not equal, and they are not quarters. The next problem has to do with reading and writing numbers. There is a specific principle or system by which we read and write numbers. First of all, numbers are read from left to right. So we have a lot of principles there. First of all, numbers are read from left to right. Numbers are read from left to right. The digits in a number are assigned place values, beginning with the one of least significance. That is located to the right. So the digits in a number are assigned place values, beginning with the one of least significance. That is the one with the smallest place value. And that one is located to the right. So we have the ones, the tens, and the hundreds. So we have ones, tens, hundreds. And everything has to do with hundreds, tens, and ones. When my younger sisters were learning mathematics at the early stage, they used to come home and ask me, "Do you know 100 tens and ones? Do you know 100 tens and ones?" I know 100 tens and ones. And they were talking about place values. Hundreds, tens, and ones. As long as you know those, then you are well on your way to be able to read and write a number. Next, a number is a list that ends after 100. That is, in the list, anything after the 100 place value is considered to be a single item that ends the list. Therefore, what we have there is 321. So, after the hundreds place value, the list comes to an end. In reading that number, we say 300, and because 21 comes after the hundreds, it is a single item in the list. We therefore say 321. On the next slide, we will take a look at what we mean by list. So do not forget that when we are reading a number, we read numbers in groups of 3: hundreds, tens, and ones. The numbers or digits that come after the hundreds place value is read as one item. So that's 321. This is what we mean when we say list. Let us list those items: a triangle, a circle, a rectangle, a pentagram, and a pentagon. So we have the triangle, a circle, a rectangle, a pentagram, and a pentagon. And the items that are in the list are separated by commas, with the exception of the last one, which is included after the word and. So when we have a list, we name them and we have them separated by commas. When we get to the last one, just before the last one, we have the word and, just like in any other list. Triangle, circle, rectangle, pentagram, and pentagon. It is appropriate to end a list with the word and. It gives an indication that the list is coming to an end. And after it, you expect just the last item. So when you are listing something, you do not say, for example, in this particular case, triangle, circle, rectangle, pentagram, pentagon. Good morning, Jerry. Oh, Jerry is just coming in. After all of the eatings, all of the problems that had to do with eating are gone, and Jerry is just coming in. So, if we do that, the list will come to an end, and will come to an end abruptly. It will come to an end without expectation. And the person who is listening on, the mind is not prepared for the end of the list. The person will expect something else. So, a list is appropriately ended with the word and coming before the last item in the list. Although reading a number is actually presenting a list of items, and it is not exactly the same as presenting a list of items as we have here, there are some very important similarities. So, presenting a number is not the same, exactly the same, as presenting a list as we have here, but there are quite a few important similarities. So there we have another number. Jerry, could you please read that number for me?
907. 900, 0 tens, and 7 ones.
Okay, so Jerry is saying that we have 907. 900s, 0 10, and 7 ones. Right. So notice that Jerry said 907. There is your number, which is a list. After the 900, there is a single item left, so we have to say and. There is no tens, so we have to say 907. Remember that after the hundreds, the numbers are treated like a single item. So 907. What do you say about that number, Jerry?
It's 400. 400, 0 tens, and 0 ones.
So Jerry is saying that that number is 400. In this list, there is no tens and no ones. There is only one item in the list, and that is the 400s. Read the number as 400. What about that one, Jerry? Read that number.
89.
Right. So Jerry read that number as 89. The list also contains one item. Those after the 100 are treated like one item. The number is therefore read as 89. 89. And that number is
67.
67. We do not typically write a number that contains no hundreds with a leading zero, like we have right here. The number is one item, and it is treated and read as 67. So if we put a 0 here, it would still be 67. Like we have a 0 right there, and it is still 89. But we do not typically write 089. Now we have another number to read. And did we say a number is a list of items, Jerry?
Yes.
A number is a list of items. Suppose our number contains another place value. How do we read it? There we have now our thousands place value. How do we read that number? Read it again as if you have a list of items. 8,321. So it is 8,321. That is how it is read. Because after the 100, what is there is treated as a single item. So there's your list coming up. 8,300, and the last item is coming up, and 21. Do not forget that the items or the digits following the hundreds place value is treated as what? One item. So we have 8,321. So remember that the tens and ones are read as one item. And remember that it is appropriate to present the last item in a list by saying and. The number is 8,321. What about that number, Jerry? Well, Jerry will learn some things today about reading and writing numbers that he never knew before. Before reading that number, there is something else that we need to know about how numbers are presented. They are presented and also read in groups of
Threes.
Right, they are read and presented in groups of 3. The first group of numbers is in reference to ones. We therefore have 300 ones, 10 ones, and 4 ones. We do not read the numbers that way, but that is the understanding that we should have. So in this group, this is the ones group, but we don't say 300 ones, because 300 or any number that we have multiplied by 1 is the same number. So 300 ones is the same as 300. 10 ones is the same as 10. And 4 ones is the same as 4. That group is the thousands group. The second group of numbers that we have is in reference to thousands. We therefore have 7 hundreds of thousands, 6 tens of thousands, and 8 thousands. This group is the thousand group of numbers. And after the thousand group of numbers, what group of number will we have, Jerry?
Millions.
Alright. So after the thousand, we will have the million. And after the million, we will have the
billion.
right. So Jerry knows a lot about those numbers in their particular groups. So the second group of numbers that we have is in reference to thousands. We therefore have 7 hundreds of thousands, 6 tens of thousands, and 8 thousands. In the thousands group, we therefore have 768. So what we have here is 768 thousands. So we read the numbers in groups of 3. And each group contains place values going up to hundreds. See, hundreds, tens. So this we have here is 768,000. Then we have 324. As we see, the maximum place value in any group is what? 100. When the hundreds are exhausted, we move over to another group. The groups are separated by commas, or an empty space is used to separate the groups. So notice that in each group, the highest place value is what, Jerry?
3, the thousand, 100,000. The hundreds.
Right. So in any group, the highest place value is the 100. And when we exceed the 100, we will move over to another group. And the groups are separated by an empty space or by making use of commas. I realize that in recent years, the groups are more separated by empty spaces rather than a comma, like what we have there. So there is a very large number, Jerry, and we will have to read that number. So if we are going to be giving it away, then I'm going to take those animations from the slides. Now, if we take these numbers out by themselves in each group, what do we have here? 174. What do we have here?
205.
And what do we have here?
768.
Right, so we have 768. So that is very easy to read, because we know that this is in the millions group, so it is 205 millions. And this is in the thousand group, so this is what? 768,000. And we know that this is in the billion group, so this is what? 174 billion. So that is how you read it. We are reading it not in order at present, but as long as you see the numbers and you know which group they fall into, it is very simple, because the highest place value in any group is 100. So it is a matter of recognizing the group that you are in. So let us throw in the others. Those are in the thousand groups. So there are two things that make a number easy to read. One, they are written and read in groups of 3. 2, the highest place value in a group or in any group is 100. So let us examine the higher place values in groups of 3. So a number is easy to read because it is read in groups of 3. So it is a matter of which group the digits fall into. A number is therefore a list containing groups of hundreds. The number that we have there is, let us read that, 174 billion 205 million 768,324. Notice that in every group we use the word and, because in each group there is a list. So each group represents a list. So a number is a list within a list. As we increase in place values, the higher place value is 1,000 times the corresponding one in the lower place value. So right here we have ones and we have thousands. So this one is 1,000 times this one. A million is 1,000 times 1,000. A billion is 1,000 times a million. So a million is 1,000 thousands, and a billion is 1,000 millions. Those on the tens slot will follow suit. 1,000 times 10 will give tens of thousands. If we multiply 1,000 times again, we will get tens of millions, and so on. So we have the same thing right here for the tens. So this one is tens, and this one is 1,000 times 10. So this is tens of thousand. And then this one is 1,000 times this one. So it is tens of million. And then this will be tens of billions. And the other one, no doubt, if we should examine it, will be the same. So we have hundreds of thousands, because 1,000 times 100, 100,000, hundreds of thousands. And then this one is 1,000 times this one, so we have hundreds of million and then hundreds of billion. So the numbers are closely, or the digits in their place values are closely related to each other. Which shows 535,206. Which shows 535,206. Now, if we are required to write that number and we have what? 1,000. Let us look over here and see what happens. What do we notice? That the thousands will be what? If we are looking at it from the right, the 1,000 is the second group of 3. So as long as we are talking about thousands, then we have 2 groups of 3s, because we have the ones group and we have the thousands group. So when we go thousands, that means we are in a second group of 3. 535,000. 535,000. The highlighted statement tells us that the largest place values are in the thousands group. If you look here, you see that 535,000. So the largest place values that we have here are in the thousands group. Any other part of the number must be in the ones group. There is therefore only 2 groups of digits. So the largest we have is the thousands. So we have this thousand group represented, and we have the ones group. So there we have our 2 groups. The ones group and the thousands group. In the thousands group, there is 500, 3 tens, and 5 ones. 535,000. 535. So we have 5 hundreds, 3 tens, and 5 ones. There we have them. 500, 3 tens, and 5 ones in the 1000 group. Then we have 206. Repeat that, please. Oh, so Jerry is saying already that it is option C, that the correct answer is option C. In the ones group, we have 261. 206 ones. So 206 ones, and what will happen to the tens? There is no tens digit. The tens slot will therefore be occupied by a 0. There it is. So with no tens is represented by 0 tens. So we need to include a 0 right there. As a matter of fact, if we did not have a 0 there and the slot was left empty, then we wouldn't even imagine how devastating that would be if we should compare that with the number that we have in the statement of the problem. So the place value right there is very important, because if we remove this one, then the number will be 26. Then this will be 526. Then this we have 3,526. Then we have 53,526. And that is nothing in comparison to what we had in the statement of a problem. The correct answer, as Jerry pointed out earlier on, is option C. Tara had $4,220.50. Which of these shows the amount of money Tara has? Tara has $4,220.50. Which of these shows the amount of money that Tara has? 4,000. Again, we will begin with the thousands group. Therefore, again, we have two groups, the thousand groups and the ones group. So there we have our two groups. Because we have 4,000, so we know that we have the thousand group and we have the ones group. In the thousands group, there are no 100 and no tens. So no 100 and no tens. Only 4 ones. No 100 and no tens. Only 4 ones. The other places will be occupied by zeros. $220. $220. 220. So we have 200s and 2 tens. There is no 1. No ones digit. Well, actually, we have to have a ones digit. Because without this place holding 0, then there is a great difference between what the number here would represent and the one that we have there will represent. The leading zeros may be discarded as they contribute no value to the number. We will also include the dollar sign. Do not forget, we are talking about money. So the dollar sign is very important. And we need to remove those 2 zeros. We don't have to remove them. But their presence there has no effect on the value of the number, so they may be discarded, those leading zeros. On the next slide, we will take a look at the cents. So we do not have the entire correct answer as yet, because the cents are missing. And Jerry is saying that The correct answer is option B. And 50 cents. So in addition to all of those dollars that we have there, there is 50 cents. Any word that contains the root cent has to do with 100. Centipede, 100 legs. But I am sure if you stop a centipede in its track, you will discover that it does not really have 100 legs. So let me ask Jerry, how many legs does a centipede have?
40.
Oh, so Jerry said that it has 40 legs. And that is why in Jamaica we call it?
40 legs.
We have 40 leg. Right, we call it 40 leg. Because they say centipede because when they look at it coming around, they say that should have about 100 legs. And the Jamaican did not take that at face value. What the Jamaican did? Stop the 40 leg and count its legs. And realize that it was approximately 40 legs. And that is how Jamaicans call the centipede 40 leg. Because a centipede or centipede really means 100 legs. Centimeter, 100th part of a meter. This time, 100th part of a dollar. So the cents in this case mean 100th part of a dollar. That's what a cent is. So we have two place values for the cents, the tenths and the hundredths, because you cannot include the hundredths place value without including the tenths place value. So we have included the tenths place value because we cannot have the hundredths place value without it. 50 cents mean 50 hundredths. 50 cents mean 50 hundredths. As usual, the place value to the left is always 10 times greater. So 50 hundredths are therefore 5 tenths. There is no additional hundredths. So when we say 50 cents, we mean 50 hundredths. And we know that the tenths are 10 times the hundredths. So that 50 hundredths that we have there is actually 5 tenths. And as we would have discovered from the previous videos, a trailing zero after a decimal point does not affect the value of the number. However, because we are dealing in cents, we need to keep those two place values ever present. Option B is correct. When representing cents, two places of decimal are always used to ensure that the hundredths place value is present. So we will always use two places of decimal in order to maintain the two places of decimal that represent the hundredths that the cents represent. What is the value of the underlined digit in 1,000? Is it 1,000, Jerry?
No.
It is what?
16,000.
Okay, so that's 16,573. Although some students may see the answer immediately, we may first write down the number that is given. Write it down from up there. Take a copy of it. We may next apply the place values. Place values are assigned from the right to the left, beginning with the digit of least significance, the one that is located to the right, the one that has the smallest place value. So begin with the ones, then tens, then hundreds, thousands. The correct answer is option D, 6,000s. Although the answer was determined already, Let us include the tens of thousands place value. There it is. Knowing place values and the format of numbers, especially that a number is written in groups of 3 digits, some candidates may determine the answer immediately. So if you understand how numbers are written and how numbers are read, then you may be able to solve a problem like this one at a glance. Which position comes just before fifth? Which position comes just before fifth? And Jerry is saying it's fourth. The numbers that we have there are ordinal numbers. They tell us the order in which events occur. For example, the order in which athletes finish a race. So ordinal numbers, they give you the idea of the order in which events occur. So they are not just numbers that are assigned, but those will tell you the order in which things occur. Position 1 is the highest position and is called first. Position 2 comes after, and it is called second. Next is position 3, and it is called third. Then position 4, which is called
fourth.
Position 5, just before fifth. Position 5 is called fifth. Just before means immediately before. The one just before fifth is fourth. Option A is correct. Some students usually confuse the larger ordinal numbers with a higher position, but the ones that are before are actually the smaller numbers. So if you finish high up in a race, is your number going to be small or large?
Small.
Right. If you finish high in a race, then your ordinal number will be
Small.
right. And if you finish way back or low down in a race, your ordinal number will be
Large.
right. So that is how ordinal numbers are represented. And students generally confuse the ordinal numbers because they are saying if the ordinal position is high, then the number is very large. Large numbers belong to the lower positions. Small numbers belong to the higher positions. As a matter of fact, you can take a look at what happens at the Olympics when you watch the race and you are also watching the medal presentation. Notice that they have 3 boxes, numbered 1, 2, and 3. And notice that the number 1 box, which is the box for the one that is first, is placed where? It is placed highest on the podium. So take a look for yourselves. Jamaica is doing well in international competition. As a matter of fact, Jamaica was just 1 gold medal from winning the World Games recently. So we know that Jamaicans are always on the podium. And when they go up to receive their medals, you will realize that the highest box is box 1, which is the first box. So the first one is actually very high. So the highest one is box 1. So the highest position belongs to the smallest ordinal number. Let us look at the order that runners in a race cross the finish line and assign ordinal numbers to them. See? they are crossing the finishing line, and we are assigning ordinal numbers. Let them go again, Jerry. This one is Jerry. No, I don't think so. Jerry is not the last to cross the line, because I think that in the statement of the problem, we had somebody else crossing the line in the 5th position. So what do we have there? Notice that this one is 1st, 2nd, 3rd, 4th, 5th. This one cross in position 1, position 2, position 3, position 4, position 5. Right. The one with the highest position is the one with the smallest ordinal number. Highest position. The one in the lowest position is the one with the largest ordinal number. Lowest position. The lowest position, which is the largest ordinal number, is one that we'll call, is the one that we call last. So the lowest position, the one with the largest ordinal number, is the one that we call last. So the lowest position is replaced with last position. Last position has the largest ordinal number in a particular set of ordinal numbers. So do not believe that if someone comes 5th in a race, that the person is last. No, if there are others in the race, the one with the largest ordinal number is the one who is last. When you count in tenths, which number comes next after 3.8? When you count in tenths, which number comes next after 3.8? Next after 3.8. Tenths. In the number 3.8, the tenth digit is the one to the right of the decimal point. So we have the decimal point. The tenths is the one to the right of the decimal point. However, in order to demonstrate how we count in tenths, we will begin at 3.0. We are counting in tenths. And when we count in tenths, the tenth place value is the one that is affected. It is the one that always increases by 1. Until there is an overflow, it will go to the more significant place value. So, however, in order to demonstrate how we count in tenths, we will begin at 3.0 instead of 3.8. Counting by tenths will cause the tenths place value to increase by 1 each time. So when we are counting by tenths, the tenths place value is the one that will increase by 1 each time, just like we have it right there. The tenths place value going up by 1 each time. Next after 3.8. What will come next after 3.8? If we continue to count in tenths, if we continue to increase the tenths place value by 1 each time, which number will come immediately after or next after 3.8? Take note, next after 3.8, which one comes next after 3.8? There it is. The correct number is therefore represented by option C, 3.9, because we are increasing the tenths place value by 1 each time. Problem number 21. What is 12 and 15 hundredths as a decimal? Because we have to read it correctly, Jerry. 12 and 15 hundredths. As a decimal. And we know that is 12 and 15 over 100 as a decimal. This tells us that the vulgar fraction needs to be converted to a decimal fraction, because the statement of the problem is saying as a decimal. So we need to convert this fraction, which is in vulgar form, we need to convert that to decimal form. And how do we do that? 100. Now we have 15 over 100. And we are dividing 15 by 100. It is very easy to divide by a power of 10. Dividing by a power of 10, the number of zeros that we have in the power of 10 tells us the number of decimal places that we need to reduce the number by. So 2 zeros tells us that we need to reduce 15 by 2 places of decimal. In a whole number, a decimal point is located to the right. So the 2 zeros there tells us that we need to reduce 15 by how many places of decimal, Jerry? 2 places of decimal. And if we had 1,000, how many zeros are in 1,000, Jerry?
3.
If we are dividing by 1,000, how many places of decimal do we need to reduce by?
3.
Okay, it's as easy as that. And if we are dividing by 10, how many zeros do we have?
1.
How many places of decimal do we reduce by?
1.
It is as easy as that. So we have 2 zeros in 100. We therefore reduce 15 by 2 places of decimal. And if we have a whole number, the decimal point in a whole number is located to the right. So we will reduce 15 by 2 places of decimal. 1, 2. The ideal way to write a decimal fraction that contains no whole number is not to leave it as it is, but to place a 0 in the whole number position. So we will not leave the decimal fraction written in that manner, 0.15. That is not good manners in mathematics. We will put a 0 to show that we have no whole number. The whole number part is equal to 0. So there we have our 0. So the number is more appropriately written as 0.15. And we do not say 0.15, but we say 0.15. And nowadays in mathematics, we notice that students are saying things like 0.15 and so on. But we know that it should be more appropriately read as 0.15. When we are reading the number, we say 12 and 15 hundredths. That is how we read it. 12 and 15, right, 15 hundredths. And means addition in mathematics. We will add 12 to 15 hundredths. But 15 hundredths is written as 0.15. So we have 12 to be added to 0.15. And in 12, like in any whole number, the decimal point is located where, Jerry?
To the right.
Right, to the right. The decimal point must be vertically aligned. That means the decimal point in 12 must be vertically aligned with the decimal point in 1500ths, which turns out to be 0.15. So we vertically align those and we add. And this is one of the easiest kind of addition that you will experience. Because in adding, what do we know? We will begin at the digit of least significant, the one that is located to the extreme right, the one that has the smallest place value, and that place value is hundredths. So 0 plus 5 is equal to 5. Add the numbers beginning at the extreme right, where we find the digits of least significance or smallest
Place value.
right. So 0 plus 5 is equal to 5. When there is a blank space in the column, we may add a 0, in which case the answer is the same, or we may say just write the number down. So when we are adding and there's a blank space, we may say the blank space or assume that it is occupied by 0. So if it is occupied by 0, we will write down 0 plus 5 is equal to 5. Or we might just write down 5. The same will occur right there. There's nothing to be added to 1. And then we have to vertically align the decimal points because the decimal fraction is present. So we have to make sure that the decimal point is included and that it is included at the appropriate position. We have 2 plus 0 and that is equal to 2. And finally, we have 1 to be added to nothing and it turns out to be 1. The correct answer is option B. No, we did not have to go through all of that in order to find our answer. But I am sticking to principle, showing exactly how we arrive at the decimal fraction and also how it may be combined with correct arithmetic processes in order to arrive at the correct answer. In a fraction, the denominator is the number that we divide by. We are dividing by 100. The 2 zeros are indicating that we need to reduce the number 15, which is the numerator, by 2 places of decimal. What is 2 and 1500th as a decimal? This tells us that the vulgar fraction needs to be converted to a decimal fraction. 2 zeros tells us that we need to reduce 15 by 2 places of decimal. In a whole number, the decimal fraction is located to the right. Let us go ahead and reduce by 2 places of decimal. On this occasion, we are proposing a quicker solution that does not make use of the leading 0. So we will not put the 0 here because our solution will not take that route. We may just unite the whole number and the decimal fraction. The whole number has the decimal point to the right and the decimal fraction has its decimal point to the left. So there we have our whole number, and what do we have there? Our decimal fraction. So we just put them together like that and we get 12.15. Because we are dividing by 100, we need to reduce by 2 places of decimal. The answer will appropriately contain 2 places of decimal after the 12. So because we have 2 zeros in our divisor, which is a power of 10, we are sure that after 12, after writing 12, we will need 2 places of decimal. We therefore did not even need to go through this process. So we need 2 places of decimal, and we just throw them in as we have them right there. If the numerator of the fraction were a number like 30, we might not have 2 decimal places in our answer. What will we do? Reduce by 2 places of decimal, as usual. This is the same kind of quick solution as on the previous slide. So if the numerator were 30, this is what would have happened. The whole number and the decimal fraction may be united as usual. Like that. Trailing zeros after a decimal fraction do not add to the value of the number. The trailing zero may therefore be removed without affecting the value of the number. So what do? Remove that trailing zero, because with or without it, the value of the number will remain the same. Apart from the removal of a trailing zero, any problem that we have like this one in which we are dividing by 100, the answer must contain 2 places of decimal. As a matter of fact, what we had 0.30, we had 2 places of decimal, but because the trailing zero after the decimal fraction does not affect the value of the number, we may remove it. But if we had a situation in which we did not have any trailing zero, as long as we are dividing by 100, which contains 2 zeros, then we should reduce by 2 places of decimal. Before moving on to the other problem, let us establish a mathematical fact. What do we notice here, Jerry?
The numerators are all 12.
Right, the numerators are all 12. And we are taking a look at when the numerators are all the same. When they are all the same. Take a look at those fractions. What do you notice about the numerators? They all have the same numerator. Numerators are equal. In a fraction, the numerator is divided by the denominator. Let us show those divisions. So we have 12 divided by 12, and the result is
1.
What about this one? The result is
2.
12 divided by 6, and the result is 2. What about the other one?
3.
12 divided by 4, and the result is 3. Next,
4.
12 divided by 3, and the result is 4. The other?
6.
12 divided by 2, and the result is 6. And finally, 12 divided by 1, and the result is 12. Do you notice anything about the denominators? Well, there are a lot to be noticed about the denominators. What do you...
They are going down smaller in sequences.
Okay, so the denominators are getting smaller and smaller. That is what Jerry said. The denominators are getting smaller and smaller. They are getting smaller each time. What about the answers?
They're going up and larger at each time.
Right, so Jerry is saying that the numbers are going up, the answers, meaning that the answers are getting larger each time. They are getting larger each time. It is a fact that if the numerator does not change and we decrease the size of the denominator, then the answer will increase. So if the numerator is the same and we decrease the size of the denominator, what will happen to the answers?
They will increase.
The answers will increase. So if the denominators are getting smaller, then the answers are getting larger. So look at this problem that we have here. Which one of these fractions shows the largest amount? Which one shows the largest amount? Is it going to be the one with the largest denominator or the one with the smallest denominator?
The one with the smallest denominator.
Right. Because when we go to the previous slide, we notice that as the denominators get smaller, that the answers get larger. Therefore, the largest amount will be represented by the fraction with the smallest, right, with the smallest denominator. So notice that in this particular case also, just like on the previous demonstration slide, all of the fractions have the same numerator. They have the same numerator. We have also established the fact that as the denominator decreases, the answer increases. The converse is also true. As the denominator increases, the answer will decrease. Right, the answer will decrease. Therefore, which one is the largest amount? It has to be, therefore, the one that we divide by the smallest number. Which one will therefore be the largest fraction? The largest fraction is represented by what option?
C.
Right, so the largest one will have the smallest denominator. The one with the smallest denominator will represent the largest amount. Option C is therefore correct. Conversely, the one with the largest denominator is the smallest amount. Which one has the largest denominator, Jerry? Which one has the largest denominator in the options?
Option D.
Right. So because it has the largest denominator, it will have the what kind of amount?
Smallest amount.
It will have the smallest amount. Remember, this is only true if all of the numerators are equal. When the numerators are all equal. Take a circle, because what we are showing here that when the denominator is the smallest, then the amount will be the
largest.
Right, will be the largest. So take a circle and divide it into equal parts 3 times. So we have 3 occurrences of the same circle. Notice that the circles are all of the same size. And that one is divided into how many equal parts, Jerry?
8 equal parts.
Right, and that will therefore represent eighths. And the other one is divided into how many equal parts?
4.
So the first has 8 equal parts. Its denominator is 8. 8 equal parts. Its denominator will be 8. The other one is divided into how many equal parts?
4.
And its denominator will be?
4.
Right. So we have that divided into 4 equal parts. The second has 4 equal parts. Its denominator is?
4.
Okay, 4. So we are talking about this one, Jerry. You've gone all the way over to this one already. And we did not write down the denominator of that one. And the other one is divided into
2
equal parts. And its denominator will be?
2.
Right. Which one of the parts is the largest?
8.
Not the denominator, Jerry. The section. Let me take a look at that in a few seconds. Each numerator is 1. This tells us that the number of equal parts that we are talking about in each case is 1. Each numerator is 1. This tells us that the number of equal parts that we are talking about in each case is
1.
Look at that animation, Jerry. Nice. Shade one part of each circle. So let us do that. Shade one part. Which part is the largest? Which of the shaded parts is the largest, Jerry?
The half.
The half, right. So it is the largest because its denominator is the smallest. Which one is the largest? The half is the one with the smallest denominator, and it is the largest one. It is the largest section. While the eighth is the one with the largest denominator, and it is the smallest shaded portion. So the one with the smallest denominator will have the largest shaded portion, and the one with the largest denominator will have the smallest shaded portion. 2 cakes were cut into fourths. How many fourths are there? A fourth is the same thing as what, Jerry?
1 over 4.
Right, 1 over 4. And what other name do we call that fraction? It begins with a Q, that fraction. A quarter. Right. So 2 cakes were cut into fourths. How many fourths are there? So 2 cakes were cut into fourths. A fourth is a quarter, which is 1 part out of 4. So we have the numerator, the fraction bar as usual, and the denominator. We are focusing on the denominator. The denominator tells us the number of equal parts in the whole. Let us divide each cake into 4 equal parts. 4 equal parts also. Let us find out the number of quarters in all. And that we will do by counting the total number of quarters in the 2 cakes.
8.
Jerry is saying that it is 8. The number or the answer is 8. Which is it? What option is it?
Option A.
Okay, that is represented by option A. There are 8 quarters in all. The correct answer is option A. 8 over 4 does not mean that we are taking 8 parts out of 4 parts. It means that we are taking 8 parts out of wholes that were divided into 4 equal parts. If we have more than 1 whole, surely we will have more than 4 quarters. So we have 4 quarters in one whole, and we have another whole, so we have 8 quarters in all. So when we have 8 over 4, it does not mean that we are taking 8 quarters out of a single whole. It means that we are taking 8 parts out of objects that were divided into 4 equal parts, or of which each was divided into 4 equal parts. Now we will take another look at the problem. There are how many cakes? 2 cakes, and they are cut into fourths. The cakes are cut into fourths. How many fourths? We may say that the cakes are divided into fourths and proceed to divide 2 by a quarter. It is just like you are saying, how many 5s are in 20?
4.
How did you get 4?
Divide.
Okay. So we are saying that we have 2 cakes. How many fourths are in that? We also need to divide. On the other hand, we are really attempting to determine the number of fourths that there are in 2. How many times may a fourth go into 2? Or how many fourths are in 2 cakes? So we are dividing 2 by 4. Just as if we say, how many 5s are in 20? We divide 20 by 5. How many quarters are in 2? We divide 2 by a quarter. When working with fractions and whole numbers, the whole numbers are written as fractions with 1 as the denominator. By writing a denominator of 1, the number is now in a form that is compatible with the fraction that we have there. Additionally, 2 over 1 or 2 divided by 1, any number divided by 1 is that same number. So 2 divided by 1 is equal to 2. Dividing by 1 does not change the value of the number, or writing a denominator of 1 does not change the value of the number. It only causes the number to be in a form that is compatible with the other number that we are using to manipulate it. When dividing by a fraction, we invert and multiply. And we will complete the multiplication process on the next slide. When multiplying fractions, we first see if there is any common factor that we may use to reduce the fractions. Meaning, if there is any number that we can cancel. So, reducing the fraction, we always say typically in the classroom, cancel. When we cancel, we are actually reducing the fractions to a lower term. The denominators are equal to 1. The fractions cannot be reduced to any lower terms. Because if we divide anything by 1, we will get the same thing. So it cannot be reduced. The answer will be the result when we are dividing fractions. The result may be found by dividing the product of the numerators by the product of the denominators. So we need to multiply the numerators when the fractions cannot be reduced, and then we multiply the denominators, and the resulting fraction or the answer will be what we get when we divide the product of the numerators by the product of the denominators. And there we have 8 divided by 1. What is 8 divided by 1, Jerry?
8.
Any number divided by 1 is that same number. So any number divided by 1 is equal to that same number. So 8 divided by 1 is equal to 8. The correct answer is option A. Two cakes were cut into fourths. We could have taken a look at our diagram and made a calculation. Each cake has 4 quarters, as we have them right there. How many times do we have 4 fourths? There are 2 cakes. We therefore have 4 fourths occurring 2 times. The 4 fourths occur 2 times. We therefore times the 4 by 2. And of course, we are saying times as in multiplication. So how many times do we have 4 fourths? 2 times. So we times the 4 by 2. 4 2s 8. The correct answer is option A. But we could have arrived at our answer much quicker. All of the denominators are equal to 4. Notice that all of the denominators are equal to 4. So we could have arrived at our answer quicker. Common sense is greater than mathematics. We could have arrived at our answer much quicker by making use of a common sense method. All of the denominators in the options are equal to 4. There will therefore be no ambiguity in our approach. That means our approach will not give us a variety of correct or possible correct as we would have had if the denominators were different. They are all the same. Therefore, when we use this particular approach, then there is only one possible correct answer that we can get. Because all of the denominators are equal to 4, in which of these options will dividing the numerator by the denominator result in our original 2 cakes? Which one will give our original 2 cakes? We have 2 cakes to begin with. 2 is 2 equal to 4 divided by 4?
No.
2 divided by 4?
No.
6 divided by 4?
No.
8 divided by 4?
Yes.
Because 8 divided by 4 is equal to 2. Then we are sure that option A is correct. Because how many cakes do we have dividing there?
2.
Right. So we use the options and the one that results in the original 2 cakes. Then we are sure that that is the correct answer. And that confirms that option A is correct. So 8 divided by 4 is equal to 2. Mathematics is the greatest subject for reconciliation, meaning that in mathematics we can do a reverse check to see if our answer is correct. We started off with how many cakes?
2.
If we make our calculations and still end up with
2 cakes.
then we must be correct. Started off with 2 cakes and we do our calculation and we still end up with 2 cakes. We are sure that we are correct. Mary was asked to write 732.8 in a table. What should she change in order to be correct? Now, some individuals might want to search the table in order to see what is wrong with it. But I do not like that approach. I prefer to write the correct thing and see how the information that we have there matches with it. So 732. In solving this problem, it is easier to do the right than to correct the wrong. Let us write the number from scratch. So we will write the number from scratch, the number that we need. We will write that from scratch. The number has 7 hundreds, 3 tens, and 2 ones. 7 hundreds, 3 tens, and 2 ones. 7 hundreds, 3 tens, and 2 ones. Point 8. Writing a number that comes after a point is not difficult, as the decimal fraction is read digit by digit. It is even easier as we only have one digit in this particular case. So writing digits that follow a decimal point is not difficult, because after a decimal point the digits are read one at a time. However, we only have a single digit, so that 8 must be the only thing that is written to the right of the decimal point. So, taking a look at that, Jerry, according to what we have in the options here, what would we do in order that this is corrected according to what we have there? Notice that the error that we have here is right there.
Right. So the 7 and the 3s and the 2s, they're all in place.
Right, they're all in place. They're all correct. So what is out?
The 3 and the 8.
Right. So what do we do then?
Put 8 in the 10th column.
Right. If we put 8 in the 10th column, then the number that we have here would have been corrected. So what we do is put the correct thing down first and see how what we have there matches with it. And that will be a very efficient, sensible way of solving the problem. Everything would be great if she placed an 8 in the 10th column. Option B is therefore correct.